Hello, everyone. Yeah. Welcome to our talk. So today we'll talk about our paper, Faults in Our Bus. So this talk is regarding fault attacks, more specifically, bus fault attack, where we use this bus fault attack to break the security of ARM trust zones. So before we start, there's a very brief introduction of ourselves. So I am Anirban, he is Nimish. So we are PhD students from the Indian Institute of Technology, Kharagpur, India. And this work was done in collaboration with Professor Debdeep Mukhopadhyay from IIT Kharagpur. So here is a brief outline of our talks. So first we'll start with a brief history of faults and literature survey on faults. Then we talk about the traditional fault points on embedded systems and SOCs. And then we present our proposal. There's a new fault point on SOCs. Then we discuss about OPTI and why it is relevant with respect to our talk. And then finally, we talk about our end-to-end attack, where we demonstrate a complete hijack of the system through fault attacks. Finally, we'll end our talk with the impact of our research work and also the takeaway from this. So what are faults? Faults are basically system errors where the adversary actively perturbs either the data or the control flow of the system in order to gain access or information about through the faulty responses. So why are faults so catastrophic? So actually, in digital systems, faults do occur, although they are rare and mostly they occur through accidents. But if they can be controlled and if they are induced purposefully, then these faults can cause errors, and these errors can be exploited to hijack the system or leak secret information from the system. Now, fault attack, and also along with that, fault attacks sometimes, if combined with other kinds of attack primitives, like for example, side channel information, as we'll show in this talk, that can lead to much stronger attack. So the literature on fault attack is pretty vast, and for the last around 25 years, there have been a lot of research on fault attacks. But broadly classifying, fault attacks can be actually classified into two subclasses, where the fault injection techniques actually concerns itself with on the actual hardware, the way you want to induce the faults in the hardware, and fault exploitation or the fault analysis, which actually it comes after you actually injected your fault. It actually depends on the type of target that you are trying to attack. Maybe it could be RSA or AES, but then the analysis technique will depend on the type of target. In this talk, we'll mostly focus on fault injection technique. So how do we, or the attackers, actually do the faults? So there are multiple ways of inducing faults, but in this talk, we'll mainly focus on electromagnetic fault injections. So we use this special kind of probes that when a current flows along this probe, it creates a magnetic field around itself. And if we go back to our elementary physics class, from the Maxwell's left-hand rule, if there is a magnetic field going on, it creates an induced current, right? And that induced current, if you place this probe next to an SOC or an embedded system where some computation is going on, it actually interferes with the circuit or with the current flowing through the circuit, and that can actually create faults. For example, if you see that for some computation, if there is no electromagnetic pulse, it creates a non-faulty execution. But on introduction of this electromagnetic pulse, it might behave weirdly, and it might create bit flips in it. So there are different types of fault models, depending on how you want to look at it. For example, if you look at from the granularity, there could be single bit fault, there could be multiple bit faults, or there could be multiple bytes, or even the word itself. But in the literature, also in the fault attack community, it was considered that for the entire register, 64-bit register, it's difficult to actually have the faults to control the entire 64-bit register. But in this work, we have achieved that entire 64-bit register can be actually faulted. And then it also depends on what type of fault you are inducing. It could be stuck at 0, where a particular bit is either stuck at 0 or stuck at 1. It could be some random bit flips. 0 goes to 1, or it could be totally random. And then it also depends on how the attacker is able to control it. It could be precise. So for example, if you are using a laser fault, laser injection to induce a fault, it is more precise. And if you are using something like EM probe, EM radiation, that does not give that much precise control over it. And then it also depends on the duration of the fault, whether the fault stays, or whether the fault refreshes for every session, or actually it stays for the entire lifetime of the device. So what are the traditional fault points that we have in literature and that is commonly considered in the community? So if we actually look at SOCs and think about all the literature that has been available to us, there are mainly two fault attack points. One is the processor itself, and the other one is the RAM. From the processor perspective, you can induce faults through external interfaces. For example, you can change the voltage, you can introduce clock glitches, which are mostly through the hardware. And also from the software perspective, you can actually change the dynamic frequency voltage scaling, or the DVFS, where you can change the frequency and the voltage that will lead to race condition inside the processor, which might lead to faults. And when you look at RAMs, there is a row hammer where you access the memory very fast that can induce bit flips because of losing charges. And then also there are EM and laser bit faults, which can actually induce flips in the memory. However, if we look from the SoC perspective, you cannot have external interfaces in an SoC, and also the DVFS itself is a privilege. And if you go into the RAM itself sometimes is protected through multiple checks, some error correcting checks, and also there are casings on top of it, which actually requires invasive depackaging, and also sometimes that depackaging process might actually destroy the chip itself. So we ask this question, are there any architectural aspects which can be used for faults, where there are no known countermeasures already employed? To answer this question, we say yes, and we find out a new fault point on SoCs, which is a system bus. So if we look at a very commercially available SoC, which is Raspberry Pi Model 3, so we can see that the system bus itself is totally uncased and is exposed. So basically, it is printed in a PCB, and you can totally observe it from top of the PCB. And why it's important? Because it is involved in all load and store kinds of instruction, where both the memory address and also the data flows between the processor and the memory all the time. So for example, this is a real-life view of our setup, where the probe is attached to next to the Raspberry Pi board. So now let us take an example of a load instruction, where we are loading something from the memory address into the destination register. So how does it work, basically? So first, the processor will send the memory address to the DRAM, to the system bus, and then the DRAM sends the data in that particular place into the processor itself. However, if you induce a fault in the system bus at that point, so the original data that is in the memory, that has got no effect. However, the data is faulted in transit. So basically, you actually induce the fault, but there is no trace of the fault. But the computation with that faulty data, that itself is affected. So in this case, since we are targeting the system bus, there could be two types of faults. One is on the data bus, where it results in incorrect data. And then there are address bus faults, which actually lead to sec faults, because of bit flip changes, you access some maybe non-existent or maybe unprivileged locations of memory, and you get sec faults. However, the important thing to note here is that for 35% of the time, we actually get all zeros in the register for the data fault. This is something which was not reported in literature earlier, and this was also considered that it is not possible to do it. So we call this as a register sweeping fault model, where it cleans the entire value for the load register. Now the point is, it seems like a very, integrity issue, right? The data is not there. But how does that integrity issue leads to a security event? So we show in this case that the register sweeping event actually can lead to an end-to-end attack on an open portable trusted execution environment, which in short is called OPT, on a ARM trust zone. Now to talk about Opti and also move you forward to the rest of the presentation and the details of the attack, so Nimish will take it over from you.
Thanks, Arinban. So, so far we have established that apart from processors and memory, where is most of the previous fault attacks focus on, you can still find a new architectural aspect on embedded systems, which is the system bus, which is also vulnerable to external fault attacks. And let's talk about one of the most interesting implications of the same. So Opti. So it's a trusted execution environment for embedded systems that closely follows the GlobalPlatform API spec and is being maintained by trusted firmware with a lot of stakeholders, including Google, ARM, Linaro, NXP, and the rest. And just like any trusted execution environment, it splits the applications you have into two worlds. The normal world, where most of the applications, the kernel resides, and the secure world, where the most security critical applications, for example, cryptography, APIs, and the rest would reside. So the TE, or the trusted execution environment, would have certain features like the memory storage would be encrypted, the peripherals would be securely isolated, the context switch would be secure, just to make sure that even if the RE, or the rich execution environment, which is the one to the left, to your right, marked in red, even if the RE is compromised by some adversary, by which I mean even if the adversary gains complete control over the RE kernel, anything that runs in the TE is still isolated and secure. So in some sense, the entire idea of trusted execution environments is to give you security even if the kernel on the RE is compromised. And I must mention that anything that runs inside the TE is coded and loaded into the TE by the original equipment manufacturer. And there are integrity checks for the same, which make sure that you and I cannot run our own code into the TE. The TE will expose its own APIs, and the most we can do is write applications in the RE, which will interface with those APIs and perform whatever tasks are needed. So from an adversarial perspective, if we are able to load our own code into the trusted execution environment, that amounts in some sense to code execution in the TE and breaks the security guarantees that come along from the trust zone that we are working with. So let's contextualize these goals a little bit more. We want the entire attack to be online, which means that we do not want the device to be offline at any point in time. The reason being that in modern IoT networks and the sorts, there are SCADA systems and other mechanisms in place which make sure the availability of the devices, the embedded systems in place. So this has certain implications. Like, for instance, we cannot attack the secure boot feature because doing so would take the device offline, and it's a bit harder to do in the sense that prior works have actually targeted secure boot, and now it's been like patched against these kind of attacks. So instead of going for secure boot, we go for the loading of trusted applications in the TE. And the second is, so when we talk about fault attacks, we need to make certain changes in the physical environment of the embedded device at a certain point in execution. So we need to know when that execution is coming up. So usually what people do is they use some code-based triggers that inform when to inject the fault. In our case, this cannot be done because the vulnerable position that we want to inject the fault at is deep inside the trusted execution environment, and we cannot inject our own code to trigger the fault injection at that point. So we come up with a combined adversary that I'll talk about in a bit that combines certain passive information with active adversary and then construct a completely non-invasive way of injecting faults. And yeah, as I mentioned, the attack must be non-invasive, which means that we should not be doing any irreversible damage to the device, like depackaging the upper layers over the processor. That mainly to evade detection later on, and also to make sure that the device is not damaged without, like beyond repair. And this means that trivial attacks like skipping instructions will not work in our case. So that's where the new fault model, which we just spoke about a while back, where you can zero out the entire value of a register while the system bus is operational, that's where we can use that. So this is the abstraction of the trusted execution environment we are dealing with. So execution begins on the exception level 0 in the normal world. That would be the upper right corner. And through a series of system calls, we go down to the very bottom, which is the secure monitor layer. That's the highest privileged layer, which performs a secure context switch to the left side. And then through a series of calls, we go back again up on the upper left corner, which is where the trusted applications are loaded. Now, in case these trusted applications require some more help from the exception level 1 on the left, for instance, some crypto library invocation of the sort, that's denoted by a key here, I believe. So it can again use those API endpoints to get its operations done. And once the tasks that the TA needs to do, they are over, we can follow the same path in reverse and send back data to the normal world side. So that's how the communication between the two worlds work. And this is where we are focusing. This is where the attack shall be mounted. So when a TA is loaded, as I mentioned, only the original equipment manufacturer can run its code in the trusted execution environment. So an integrity check is done, which is just a signature verification. If the binary succeeds the verification, in that case, 0 exit code is returned. Otherwise, some error is raised and execution is aborted. So let's say if we want to load our own trusted application into the trusted execution environment, in that case, we need to somehow do something with this signature verification. And just like we mentioned, some of the other fault attacks, which could help us by skipping this verification or polluting the results of the execution, mainly are not available in the context of SOCs like Raspberry Pi and the sort. And one thing I want to mention is that the signing key is not stored on the device by the manufacturer. So there's no question of stealing those keys and signing our own applications. However, we want to mention that if the signature verification fails, in that case, the fault model that we just discussed, where we fault the system bus itself, it could actually be used to convert a non-zero value to 0 and thereby bypass the integrity check completely. Note that this is not an instruction skip. We are not skipping the check. We are changing a non-zero exit code to 0. And by standard Linux convention, 0 means a success. So this is how it looks like. We have a cipher RSA verify function that stores, and following it is a store instruction that stores the exit code somewhere on the stack. And later on, this same address is being loaded back into W0 and a compare with an immediate value of 0 occurs. And if that works fine, then if that works fine, then the execution proceeds just normal. Otherwise, it aborts. So we mounted the attack on this particular point in execution. And sometimes no effect happens. Sometimes there's a partial success, which means the value did change, but not 0. But sometimes we did observe the register value W0 to be completely 0, or to be completely changed to 0. And this allows us to mount an end-to-end attack. So basically, load the adversarial TA into the trusted execution environment through false, and then redirect communication that is meant for other TAs to the maliciously load TA that we have, and then decrypt that. So basically, this means that any other TA in the system, its communication is, its encrypted communication is now available to the adversary. So the first phase, as I mentioned that we need to understand when exactly to inject the fault. And we cannot use any explicit code triggers in the Opti kernel to inform fault injection. So what we do is we attach a separate set of instruments that allow us to observe the power consumption of the embedded system under question. And this helps us identify when exactly in execution the RSA signature verification is happening. Here's a oscilloscope output of the same. And this allows us to inform fault injection, which is on the right here. So to unpack the first signal on the top, and the second peak of the first signal is where the instruction execution is happening. And the last instruction, the last signal, the third signal is the fault injection basically. So you can see the second peak of the first signal is more or less aligned with the last signal that we have. And the last signal is the set of pulse trains which actually amount to the fault injection. So what we propose is that if we use a power side channel as on the left, then we can use that to inform and align our fault injection with the move instructions or the store or the load instructions in place. And this is a schematic of the same. So with fault injection, we change a non-zero value to 0, which is later loaded and compared for the signature verification to succeed. And as evident, this fails and loads the malicious TA into the trust zone as we have. And this is the entire combined adversary that we talk of. So we use both the power side channel analysis plus fault injection to load the TA into the system. And this leads to code execution in the trusted execution environment that we have and amounts in some sense to privilege escalation. So now we have code execution in the trusted execution environment. We like to use that to compromise the communication that is meant for other TAs in the system. So how do we do that? So a brief on how communication or how execution happens in the trusted execution environment. The insecure world, if it wants some help from the secure world for like operations like cryptography or the sort, it invokes a certain TA, which is uniquely identified by a UUID, a unique identifier, and that TA is loaded into the trusted execution environment and performs its task. Now, the API spec on which Opti and many other trusted execution environments for embedded systems are constructed, they give the responsibility of choosing the UUIDs or the unique identifiers of the TAs to the equipment manufacturer. Now, here is a very important assumption that is in play. So recall that in the trusted execution environment, only the OEM or the equipment manufacturer can load their own code. So it makes sense that the OEM will choose the identifiers that will not collide with each other or will be unique. And as a result, the behavior of the system when two TAs, they share their unique identifiers, or when the unique identifiers are same, that's undefined. And in our experiments, we found that if this situation indeed arises, then a non-persistent trusted application is preferred for execution over a persistent trusted application, where persistence is just like a server client scenario. Whether you shut down or whether you remove the resources that the server has after the client closes the session. So the persistence is defined in the same sense. And this is where we chain the two attack vectors. So from the first attack vector, we load a TA into the system, make it non-persistent, and make its identifier collide with another identifier in the system, and redirect communication meant for some other TA to our own TA. But I must remind that this communication, even though we have been able to redirect it, this communication is still encrypted. So now comes the question of decrypting it. So there exist third-party extensions which do key management, symmetric key management, which is used to protect this communication. These extensions, they do not allow adding debuggers or just reading out the key. They do not allow unauthorized reads to data pages that hold the key. And they look something like this on the left. So whenever keys are needed. A key transfer request goes to the extension. The keys are transferred. And after the operations, a key surrender happens, and post that, the application can proceed with sending the encrypted and the signed communication to wherever they want to. However, our observation here is that this does not extend to segmentation faults. And recall that the attacks that we discussed, that sometimes through bus faults, when the address of the memory being accessed is incorrectly faulted, we were able to handle 6F signals. So it turns out that if this situation does arise before key surrender, then in the codums file that follow, we have the entire key readout. And again, since the communication channel was protected by symmetric key management, doing this on the normal world side, where the adversary has control over the kernel, also compromises the keys on the secure world side. So a bird's eye view of how the entire three attacks are chained together. So assume you have a TA, machine learning maybe, that you want to compromise. The first step is on the very left, where you use the faults to load your own TA into the trusted execution environment and gain code execution there. The second step in the middle is to make sure that the identifiers for the TA that you have loaded, it collides with the identifier of the victim TA that allows redirection of communication. And the third step is to induce these segmentation faults before key surrender to get the signing keys and the encryption and the decryption keys. And from there, you can simply just decrypt communication, and if needed, re-sign it also and forward it if needed. So that's how the entire three attacks chain together, and they break the security guarantees of OPTI, which transitively follows the GlobalPlatform API spec. So we found that any trusted execution environment that follows the spec is also vulnerable to the same attack. So a very quick note on the impact. We reached out to Linaro, which maintains OPTI right now. We have a CV here, and we also worked with them to deploy a countermeasure for the same in the OPTI kernel. So this is a snap of the countermeasure that we jointly developed. And I'd like to draw attention to the last function call here. So in some sense, it's a fault mitigation set check result not 0. So this is in response to the fault model that we introduced. And the idea is to maintain some stateful information and check when the error code or the result of some operation is not 0 when it shouldn't be 0. So that's the exact thing that we were trying to do. And a very quick idea about some other implications of system bus faults, specifically in the context of embedded systems. We were also able to re-enable attacks on AES that follow T-table implementations. They were, in some sense, prevented ever since defenses came out against fault attacks on processors and memory. And we were also able to use the address bus faults, which was the segmentation fault attack, the third attack that I just discussed. The same attack can also be used to break masked PQC implementations like Kyber and the same. So PQC implementations like Kyber, they are the standards as we move to the post-quantum world that NIST has already standardized. And it seems like that although algorithmically everything is fine, but when we go to implement the same, we implement all the shares of the secret key in one C or C++ like structure. So one fault will be able to leak all the members of the C or C++ structure, and you get all the shares. And if you get all the shares, you can combine them and leak the key directly. So takeaways. When designing the system, it's not just the system, but also the execution environment that comes along with it. This is specifically important in the context of embedded systems, which are supposed to be secure even without human supervision. So that's where physical adversaries come up, side channels, faults, and these kind of attack vectors are also there. Secondly, the new fault model that we came up with on system bus. So prior to this, only faults on processors and memories were considered, but system bus is also something that we show can be faulted. So that's also something that needs to be kept in mind. As I mentioned, we did it on Opti, which is just one implementation of a trusted execution environment spec, but what are the implications for other systems that also run on similar embedded devices? And thirdly, API spec should be, or rather, we propose to be rethought in light of adversaries that can do SCA and FI. The reason being, as I mentioned, the reason we could do the second attack was because the API spec was assuming that only the OEM or the equipment manufacturer can load their own code into the trusted execution environment. And they left the responsibility of identifier collision onto the OEM, basically. But if that assumption is voided because of some attack like this, then any security that is derived from the assumptions, that stands void. And I'll end with, so this is the setup that we used for this entire work. And the capabilities of this setup, they have like side channel analysis, power and both electromagnetic side channels, fault attacks, fault analysis, and to some extent also microarchitectural attack analysis. So thank you. And if there are any questions, then we can have them. And thanks a lot for listening. Yeah, thank you.